Welcome to Spring LIB.
Okay, so this is kind of a fun problem. It gives you a situation for light interference, two-slit interference, and they want you to construct the same thing, but for a sound wave. So I'm kind of interested in seeing what the result is. So we know, let's get the givens down first. We know that the frequency of the light is 4.6 times 10 to the 14 hertz. And we know the slit separation is 0.1 millimeters, 0.1 times 10 to the minus 3 meters. And okay, and then we have this certain set of angles, and we want that to be the case for F is 262 hertz. So Fs is 262. So let's look at the equation that sets the set of angles. So we know that for two-slit interference that d times the sine of theta is equal to m lambda. So let's see. So we know that the angle set is the same. So then we can say sine theta let's just bring all this stuff that has to do with this set of angles onto one side. So we can say that that's equal to lambda over d. So lambda over d is going to really set where our angles are. Let me just stop and think a bit. I'm going to pause. Okay, I think we're thinking about it. I don't think it makes sense to move this m over. What if we try to solve a simpler problem and just say that, look, we want their first angle to be the same, so that's m equals 1. And then I think, if your first angle is the same, there's no reason why in this equation that your second and third angle wouldn't be the same, because it just sort of scales with m. And so let's just get the first angle to be the same. Well, actually, I mean, we can just put this m back over here, and then just keep in mind, if we want all the angles to be the same for the different m is 1, 2, 3, 4, we need lambda over d to be the same. So now let's figure out what lambda is in terms of frequency. So some just kind of a side equation. Frequency is c over lambda, and c is the speed of the wave, lambda is the wavelength. Let's see, meters per second divided by meters. Yeah, I always remember this kind of by units, or at least I check my memory. So let's go ahead and put that in there in terms of frequency, because that's what we have. So lambda is c over f. So that's going to be c divided by f times d, where d is the slit separation. And again, we want this to be the same. So then we want c of light, f of light. So let's call this f up here. And then d is to be equal to, I guess, d for the light situation. And then that's c for the sound, f sound, d sound. And so we can then use this to solve for d of the sound. So I'll do that up here. So we can say d of the sound is equal to just kind of cross multiplying c of the sound, f of the light, d of the light, and divided by c of the light, f of the sound. So let's see. So I think speed of sound is 343 meters per second. So we can write that down. I'm just going to double check that because it's just kind of off my top of my head. Speed of sound. Yeah, it is 343 meters per second. Okay, great. And then the speed of light is 3 times 10 to the 8. And then how many sig figs do I need? Just 2. Okay. So I'm going to pause while I put all these numbers into my calculator. Okay, with that, I get 200 meters. It's kind of interesting, actually. It's like a really, that's really far apart. Yeah, I'm actually kind of interested what kind of setups you can have. Because it'd be really hard to have a 200 meters separating like two slits and have your sound wave be like coherent across that. So, I mean, I guess it would be easier perhaps to do like a wider angles if you're bringing them closer together. But anyway,